So the feedback earlier this week, a lot of people, or a couple of people, mentioned going through some more exam paper questions. So if you want to have a look at some questions yourself, it is questions 6 and 8 in the exam papers you're going to be looking at. The reason I haven't been assigning you too many of them is that it's only bits and pieces of the questions that you can do at the moment. A lot of them are going to require you to finish chapter 21, which we're going back to next, and to have completed chapter 23 as well, which we'll go on to afterwards. But if you want to have a look through them, question 6 and question 8, and if there's any in particular that you want me to go through, that you feel like you could do a lot of it, but you want me to go through it just to see, then let me know. And if videos like this one turn out to be helpful, I'm more than happy to do more of them. So one I've chosen here that we can do A, B and C. We can't do D and E, but that's only 11 marks of it. So it's 2018 question 8. And I've started off here a little bit for question A, and we'll just go through finishing it off now. So A part 1 is draw the structures to show all the bonds and molecules B and C. The key phrase here is showing all of the bonds. So I haven't drawn in my hydrogens here, you have to. It's just I'm trying to do this on the touch screen, so it'll take me ages and my H's will look really bad. So you have to show all of the hydrogens, and you have to show all of the bonds here. So B, I'll tell you what I mean by that. B is propan 1-ol, so I have my 3 carbons. 1-ol means that on the first carbon, I'm starting at the right numbering here, I've got an alcohol. So that means I've got my hydroxyl group. Now, we said during the PowerPoint that you can show the hydroxyl group by just writing OH. In this case here, you can't. You can't just do that because, as we said already in the question, they asked you to show all of the bonds. So you'll have to write in O and you'll have to write in the separate H. So you have to show that bond in there or you won't get your marks. And then I just fill in my other hydrogens that I'm going to need there. Then for C, C is propan-al. We know that al, an ending of al, means that it's an aldehyde. So we've got the CHO group at the end. It's written CHO. So we're going to have a double bond to oxygen and a single bond to hydrogen. Remember, it didn't tell me a number. It'll never tell you a number for aldehydes because the aldehyde, the group has to be at the end because you have to have this hydrogen attached to the carbon with the oxygen on it. So you will always have your aldehyde group on the end carbon. So that's part 1. A part 2 is which one of the 4 compounds contains only tetrahedrally bonded carbon atoms, or only one tetrahedrally bonded carbon atom. So the rule here is that a tetrahedrally bonded carbon atom is a carbon with 4 single bonds. So remember when we were doing our shapes, well, I didn't do them with you, you'd have done them last year. The shapes of your molecules, tetrahedral means 4 single bonds. So this carbon has 4 single bonds, this one does, and this carbon does. So they are all tetrahedral. You have 3 tetrahedrally bonded carbons there. This carbon has 4 single bonds, this one has 4 single bonds, so they'll be tetrahedral. However, this carbon has a double bond to it, so that's going to be planar. So anything with a double bond is going to be planar. I've also drawn out A and D over here. A is butane and D is ethanoic acid. And so if we just go through those again, that's going to be tetrahedral, 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 tetrahedral. So you have 4 there. Here, this is tetrahedral, and our planar carbon here is planar because it has a double bond. So our orange ones there are planar. And so the question asked you which molecule only has 1 tetrahedrally bonded carbon. So your answer is D. You weren't asked to draw all of these out. So if you had just kind of figured it out in your head and you wrote down your answer, that's absolutely fine. So D is your answer there. A tetrahedrally bonded carbon means 4 single bonds. Any carbon that has a double bond coming from it, if it's double bonded to oxygen or double bonded like an alkene, they are planar carbons. So question B is some definitions. First of all, explain the underlined terms. So I'm not going to attempt to write these out on the touch screen, but I'll just talk you through them. So structural isomers are two molecules that have the same molecular formula but different structural formulas. So there would be 6 marks, going for that definition. 6 marks for that. 3 marks for saying that they have the same molecular formula, 3 for saying that they have different structural formulas. Or you could say that they have that the atoms are arranged in a different way instead of saying structural formulas. The other one is primary alcohol that's underlined. So primary alcohol is one that has one carbon attached to the carbon with the hydroxyl group. So our alcohol is going to look like this, drawing out all of our bonds. And if this carbon that's got the hydroxyl group on it is bonded to only one other carbon, that's a primary alcohol. So you could say that about it being attached to only one other carbon. You could say that the alcohol, the hydroxyl group, is on the last carbon in the chain, because then it's going to be only attached to one other carbon. Or you could say that it has 2 or 3 hydrogens attached to it, because obviously it's going to have at least 2 here, and if the carbon wasn't there, it would have another hydrogen to make it methanoic acid. So that's your other option there. There's a couple of ways you could say that. The one we mentioned though was that it has one carbon only attached to the carbon with the hydroxyl group on it. Part 2, C and another compound E are structural isomers. Draw a structure for E. So there are loads of examples of this. So you could have several different answers here. The main one that I would suggest is that C is propan-al. So an aldehyde, we know they were partnered up in the video with ketones. So if we always think that an aldehyde, there's always going to be a structural isomer that's going to be a ketone. So my propan-al is the formula, so I drew it out earlier on, is C3H6 and O1. That's my molecular formula. That's the number of atoms that I have. And if I try to convert my aldehyde into a ketone, the only difference is in a ketone is that we need to have the oxygen in the middle. So our aldehydes, we need to have the oxygen attached to a carbon that has a hydrogen attached. In a ketone, the carbon with the oxygen on it is attached to only carbons. And so if we fill in the blanks to make sure every carbon has 4 bonds to it, you can see that if you count that up, that structural formula also fits in with this molecular formula. There are lots of other options. If you have a look at the mark scheme for this, they've given out loads of options if you want to try to draw out a couple more. But I would always suggest that if you see an aldehyde or a ketone and they ask for a structural isomer, give the opposite one. Aldehydes and ketones can always be interchanged. And part 3 in B is give the name for E. So IUPAC just means name it the way we've been naming it. So we have 3 carbons, so it's going to be prop. And all the carbons are joined together by single bonds, so don't forget to write in propan. And we know that the ending is going to be -one for a ketone, but we must also take into account which number carbon the carbonyl group, the oxygen and carbon group there is at, and that's on 2. Now, in this example, because there's only 3 carbons, That's the only place you could possibly put it to make it a ketone. So you don't actually have to give the number, but I would say just give the number every single time. You can see in the question over here for B that they gave the 1 in propan 1-al, even though you don't need to. I would give the number every single time, just so you're never caught out for it. Part C then is explain clearly why the boiling point of propan-al is much higher than that of butane. So the reason for that, propan-al has dipole-dipole forces. So if we look at the structure of propan-al, the ending of it, so I'm not going to draw out the whole thing, but the ending of propan-al, of an aldehyde, so this would work for any aldehyde, we do have polarity here. So in this we've got the delta minus on the oxygen, and we've got a delta plus on the hydrogen. So what that means is that those can form dipole-dipole forces between the aldehyde molecules, making it more difficult to separate those molecules, which is what you're doing when you're boiling them. So for that one, because C is worth 12 marks, it's 6 marks for part 1, 6 marks for part 2. So you do need to specify that propan-al has dipole-dipole forces, or is polar, it has polarity, whereas butane has weaker intermolecular forces. So that's only going to have van der Waals forces, it's non-polar. So you need to, if they're asking you to compare two things, which is what this question is asking you to do, and you see that there's a lot of marks going for it, even though it might seem obvious to say that propan-al has stronger intermolecular forces, you still need to back that up by saying butane has weaker ones. And then part 2, the boiling point of ethanoic acid is higher than that of propan 1-al. So looking at our ethanoic acid and our alcohol groups, if we just draw those out. So ethanoic acid, so again I'll just draw out the alcohol functional group. And that's the ethanoic acid functional group. And then propan 1-al is going to have the hydroxyl group on it. And the question, ethanoic acid is higher. So ethanoic acid has stronger hydrogen bonding because there's 2 places for the hydrogen bonding to occur. So it has stronger hydrogen bonding because it has the polar OH group and it has the polar carbon-oxygen bond. So you need to point that out. You need to say that ethanoic acid has stronger hydrogen bonding because it has 2 areas of polarity. You could also say that it's going to allow it to form a dimer, which we've seen in our notes as well, where you have 2 ethanoic acid molecules forming very strong hydrogen bonds. So what that would mean is that you would have another ethanoic acid, let's change the color, you would have another acid group here, like this, and what you would get is you would get the very strong hydrogen bonding between these different parts of the molecules. So that's the reason that your ethanoic acid has a higher boiling point than propan 1-al.